Good day, my name is Mcn, student number 28131192, and I'll be representing group number 37. Welcome to our fluid mechanics experiment on sluice gate flow analysis. In this setup, we explore how water behaves as it passes beneath the sluice gate in an open channel. By applying Bernoulli's principle along with different streamlines, we'll derive the downstream velocity in terms of the upstream and downstream water height, which is capital letter H and small letter h. This experiment helps us understand real-world hydraulic structures and the dynamics of inviscid flow in open channels. Let's dive into the physics behind the flow. Thank you.
Good day, my name is Mecn, student number 2809206, representing the setup and objective. In this experiment, we analyze water flow beneath the sluice gate in an open channel. The upstream water level is capital letter H and the downstream level is small letter h. Our goal is to determine the downstream velocity using Bernoulli's equation, assuming inviscid flow and negligible upstream velocity. Thank you.
Good day, my name is Moni Khanyafo, student number 2672335. Continuing from my group member statement, Bernoulli's equation relates pressure, velocity, and elevation along a streamline. Since the flow is inviscid and V1 is approximately 0, we can simplify the equation to compare energy levels upstream and downstream of the gate.
My name is Shalom Marutla, student number 2740702, and I'll be continuing from where my previous colleague has left off. First, we apply the Bernoulli's equation along a streamline at the top of the flow. Upstream, the energy is mostly due to elevation, capital letter H. Downstream, the elevation is small letter h and the velocity is v. We have used the equation that has been given to us to solve our problem.
My name is Khalaletan Lidira. For streamline along the bottom, we apply Bernoulli's equation along the bottom streamline. Here, both upstream and downstream points are at the same elevation, so the energy difference is purely due to velocity. This gives us V is equals to square root of 2g capital H. This assumes that bottom pressure remains hydrostatic.
My name is Mahaura Patelo, student number 2856810. So basically, in conclusion, the downstream velocity depends on which streamline we analyze. These results help engineers design hydraulic structures like spillways, floodgates, and understanding flow behavior is key to managing water resources efficiently. Thank you.
Now on the results discussion. The objectives of this investigation were successfully met, as both theoretical and experimental approaches were used to study flow under a sluice gate. Theoretical analysis using Bernoulli's principle provided an ideal prediction of downstream velocity, while a simple low-cost apparatus allowed for practical measurement of flow parameters such as upstream head, gate opening, and actual velocity. The results showed that theoretical velocity were much higher than the actual measured values for all gate openings due to real fluid effects like viscosity, turbulence, and flow separation, which cause energy losses not accounted for in the ideal model. As the gate opening increased, both theoretical and actual velocity slightly decreased, aligning with the expected trend from Bernoulli's principle. Overall, the experiment clearly demonstrated how real flow deviates from ideal prediction, fulfilling the study's aim of linking theoretical understanding with real-world fluid behavior.